All right, let's dive right into this explainer. Today, we are completely rethinking how we learn math. Seriously, I want you to imagine you aren't just sitting at some desk with a pencil and an eraser. Instead, you're walking through the doors of the Meridian Space Agency. You're part of their flight dynamics group. Now, the pilots, sure, they might actually fly the rockets, but you are the one who decides if those rockets are actually safe to launch in the first place. This is the whole premise of a genuinely fascinating 15-day high school calculus simulation called the Ascent. Because let's be honest, for so many of us, calculus was just this massive, endless stack of worksheets. You know the drill. You solve for x, you find the derivative, you check the back of the book, and if you get it wrong, well, your grade drops. It's totally abstract. But what if calculus wasn't a worksheet? What if it was quite literally a vital survival tool? In the Ascent simulation, the math you do dictates if a multi-million-dollar space mission flies safely or if it ends in total catastrophe. The stakes are completely flipped on their head. So the crucial point here, the entire philosophy of this simulation, really boils down to this one core idea. When calculus becomes the tool for deciding whether something is safe to attempt, rather than the punishment for being wrong on a worksheet, students start using it like adults. That right there is the core philosophy. Over the course of 15 days, students are broken up into these tight-knit teams of flight dynamics analysts, and they're using real calculus, not as some annoying academic hurdle, but as the absolute ultimate safety constraint.
Section 1. 4 epic space visions. Escalating stakes and mathematical pillars.
And this brilliantly illustrates how they pull it off. Students actually take on very specific roles: lead analyst, mission engineer, mission communicator, and they have to guide the Meridian Space Agency through a carefully structured season of spaceflight. We're talking 4 3-day arcs where the missions get significantly harder. They kick things off with Starfall, which is a low Earth orbit satellite mission relying heavily on derivatives and the Tsiolkovsky rocket equation. Then comes Lifeline, an ISS resupply utilizing integrals. Next up is Artemis, this incredibly tense, crewed lunar mission demanding constrained optimization. And finally, the big one, Horizon, a Mars cargo drop that forces students into some really complex modeling under uncertainty. So as you can see, the math scales up right alongside the danger. Section 2, the traps of cognitive bias. Experiencing the fallacy. Now, the absolute pedagogical genius of the Ascent is this one strict rule. Students literally must fall into a cognitive trap and make a mistake before the teacher ever gives that bias a name. Let me show you how this plays out right off the bat in the first mission, Starfall. The students are asked to calculate the velocity needed to get a satellite into orbit, right? So using their clean, perfect textbook formulas, they confidently calculate a pristine 7,670 meters per second. But as we know, space isn't a textbook. Gravity, drag, atmospheric resistance, those things actually exist in the real world. The realistic velocity they need is actually 9,170 meters per second. Guys, that is a massive 20% gap. So the students submit their textbook numbers, they launch their rockets, and they have to watch them barely scrape into orbit with almost zero fuel left. Or, just fail completely. Now, what's really interesting about this is that only after the students have kind of panicked and realized their rockets nearly crashed does the teacher actually step in and reveal the culprit. It's the planning fallacy. This is defined as systematically underestimating the time, resources, or difficulty required for a future task. See, the students didn't just miscalculate some numbers, they fell into a deeply human psychological trap. They basically assumed real-world physics would be just as frictionless as their homework. Section 3. The Artemis Crucible, high-stakes decisions. So, once they've learned that lesson the hard way, the simulation really tightens the screws. Jump to day 8 of a crewed lunar mission and an unexpected anomaly hits. A pressurization valve fails. Suddenly, the student teams are staring down 2 options on a ticking clock. Option A is a contingency abort. This guarantees the crew gets home safe, sure, but they lose 18% of their scientific data. Option B, on the other hand, is to push forward and try a super risky propellant transfer. If it works, they save all the science, but if it fails, there is a 14% probability of catastrophic crew loss. 14%. As you can imagine, the tension in the classroom at this point is just immense. The students have spent 8 grueling days planning this mission. I mean, they want the win. But the simulation's flight director provides this absolute, non-negotiable constraint. Crew lives are not negotiable. Mathematics that suggests otherwise is wrong mathematics. And this right here teaches students the real language of mission control. You simply cannot treat human lives as a variable in an expected value calculation. The safety constraint absolutely must hold. And yet, so predictably, some teams will look at their 8 days of hard work and vote to push forward anyway, relaxing that safety math just to save the science. Only after the dust settles does the teacher reveal what's actually happening here. It's the sunk cost fallacy. Continuing a plan because resources have already been invested, even when new data says the plan should absolutely be abandoned. 8 days of investment should never, ever justify a 14% risk to human life. But in the heat of the moment, the human brain just desperately wants to protect its sunk costs. Let's move to Section 4 and see how this builds. Rewarding reasoning over luck, the DOC rubric. Because think about it, if you're constantly punishing students for making mistakes, they're just going to stop taking risks altogether. So how do teachers actually evaluate this intense, bias-filled environment? Well, they focus entirely on rewarding reasoning over luck. They use something called the Decision Outcome Coherence, or DOC rubric. And honestly, this is brilliant. The DOC rubric scores the team's reasoning, not the ultimate outcome of the space mission. So if a team honors those safety constraints and makes a mathematically sound choice to abort, but they still get a bad random outcome in the simulation, they actually score incredibly high. Conversely, if a reckless team totally ignores the math, pushes forward on momentum, and just happens to get lucky and survive, well, their grade drops. It evaluates their analytical discipline, completely separating their logic from pure chance. And this grading philosophy becomes absolutely critical in the final mission, Horizon, where they have to land cargo on Mars through a really unpredictable atmosphere. To survive a very messy 15% atmospheric variance, they have to follow 3 key steps. Step 1, model multiple scenarios. Step 2, test their math for fragility. And step 3, most importantly, favor simple, robust plans. This specifically trains them to overcome complexity bias. You know, that false belief that adding a dozen complex variables somehow makes a model better. On Mars, simple and mathematically honest plans are the ones that actually win out. Which brings us to the ultimate takeaway of this explainer. The Ascent uses calculus to reveal how our own brains kind of trick us, whether through unearned optimism, sunk costs, or just unnecessary complexity. By actually experiencing these traps firsthand, rather than just memorizing some definitions out of a textbook, students build genuine analytical resilience. So, I'll leave you with this final thought. How might recognizing your own cognitive biases, like not just knowing they exist, but actually feeling them in the moment, how might that change your real-world decision-making? Think about that the next time you're weighing a tough choice. Thanks for joining me, and keep questioning your assumptions.